But thank you. Good, good evening, Lucky. Yesterday's class. Then, R2R. In that, what we are going to discuss is having the name voltage switched R2R. What is its name? Voltage switched R2R. Now, listen here. Let me draw the figure first. So, first, I am doing what we call 4-bit R2R DAC. What are the different type of resistors? R2R can be there anytime for any resistor. Like that, wide range is not required. Only two type of resistors are there here, R and 2R. Or ladder type DAC. Okay. Now, because it is an ideal op amp, what is the input current? 0. So let me take this voltage as VA. If it is VA by virtual ground concept, this is also VA. As I told yesterday, for non-inverting amplifier, what is your formula? 1 plus R2 by R1 into VA. So your job is very simple. Find the equation and prove that. What you need to prove? V not equal to resolution into decimal equivalent. Yes, we need to prove it as RD. Very good. So now see here. Now I want to give you one important shortcut which we discussed in the network analysis. You have a voltage source and resistor and another resistor. Now, what is the equivalent? It is you should keep this in your mind whenever you have a resistor. Okay. If you have this kind of circuit, always this is the equivalent. If you have a voltage source series with resistance parallel with another resistance, what is the equivalent? V by 2 series with R by 2. It can be anything. This voltage can be anything. Yeah, Thevenin's you can do, source transformation you can do, any method you can do it and prove. Because it is not networks class, I'm not going through that. But keep this in your mind. We can prove this by n number of ways. By Thevenin's, you can prove. By source transformation, you can prove. Different ways are there to prove it. It is true only if both the resistors are same, you can replace by R by 2. Okay. And this voltage will become half. For example, you have this, what is that? V by 2 series with R by 2. Again, parallel with another R by 2. What is the answer? No million. Okay. V by 4 series with R by 4. Like that. Okay. So these are the example. If it is not R by 2, if it is R and R, we take R by 2. If it is 2R, 2R, we take R, whatever may be. So let's go to the original problem. Now in this question, I want to find VA. So what is VA? Okay. So I want to find what is VA. So here, how many inputs are there? 4 inputs are there. I will apply only one input at a time. First I will apply D3, then I will apply D2, D2, D1, D0. I will apply only one input at a time and I will find the response by using superposition theorem. So what is that? By using superposition theorem, if only bit 3, that is your D3 is applied and remaining. Okay, audible? Okay, listen. Stop that discussion. Aditya, you want me to repeat the entire course? Okay, no problem. Just go back and play your all audios, videos from first day. Full course chahiye. Everything is available here. You can go and play a number of times. Okay. Okay, leave it. Come here. हिंदी में भी डिजिटल नहीं हुआ. So listen here, we have only D3 applied. Please listen, remaining bits. Remaining bits equal to 0. So what is the circuit you will be having is like this. You have a 2R. First input is anyway, first line is ground only. Then another 2R. What is this? R and 2R. Again R, 2R. And here again R, 2R. Okay. Now here you have connected bit 3. Bit 3 is replaced by VR into V3. What is VR? VR is voltage of logic 1. What is VR? VR is the voltage of logic 1. You understand this or not? Okay. Very good. So now, 1 minute. Now, listen here. So here 2R, you just tell me 2R parallel with 2R is how much? R. R series with R, 2R. 2R parallel with 2R, R series with R, 2R. So this part is equal to 2R. Again parallel with 2R is R. Series with R is 2R. So 2R parallel with 2R. What is the answer? No. Up to this, it is 2R, okay. But don't take this 2R and this 2R parallel. No. Final one is having source. Okay. It is not in parallel. It is having source in between. Okay. So it is slightly becoming like a networks class. Don't worry. So 2R parallel with 2R VR into V3. This will give you VA3. Okay, if I take this as introduction, no one will join the class. Okay, actually for this topic, generally networks knowledge is required. Okay, because measurements or whatever may be, networks knowledge is required. Here I am not directly using. In my class, I never use anything directly. Everything I give and use. I derive and use. Okay, now listen. Let's use this formula. Voltage source series with R, parallel with R. So voltage source series with resistance, parallel with resistance, both are equal, na? 2R and 2R. So what is the equivalent here? 2R and 2R. What is the half of 2R? R. What is this voltage? VR and V3 by 2. This is your VA3. What is that? Is the voltage when bit 3 is 0. Bit 3 is applied. Input current of op amp is 0. You know this condition. So now what is VA3? If there is no drop, because current 0, no drop in this resistor, this voltage and this voltage must be same. So what is the answer here? VR V3 by 2. You understand? Please tell me. Very good. So what some control system discussion is going on when my net is gone? Rudraksh, you want previous slide? Rudraksh, please ask any doubt. Okay. No, I don't teach controls. Controls is taught by our Ajay sir. Okay, okay. I think Rudraksh is having some doubt in previous slide. Any doubt, please ask. Is there or went? I take only networks and digital. Okay, digital microprocessor networks. Right now I'm taking only this. He was having, where is he? Is there or went? Yes, yes, yes. Past time I think he went. Sir, one show previous whole circuit op amp, please. Okay, no problem. See here. No problem. You can enjoy when it during past time. What can you do? These are the supply bits. D3, D2, D1, D0. Anyway, it is having that biasing voltage will be there that we don't show here. Okay. And listen here. Here we are applying the bits. Now these bits are giving either 5 volts or 2 volts, whatever maybe. Logic 1 is 1 volt, logic 0 is some other volts. Okay, Sushil? Right, fine. So now similar analysis is to be done for D2. Then I will conclude. If only, anyway, I took the screenshot, so no problem. If only D2 is applied, remaining all bits are 0, then what happens? So now remove this and apply here data. So make it ground and here you apply VR into V2. You understand the difference? Earlier you applied this. Now you applied only this one. Okay. Is it clear up to this? So now let us see how to analyze this condition. How to analyze this condition. Now see here again same story. Up to this point, 2R parallel with 2R is R, series with R is 2R, parallel with 2R is R, series with R is 2R. So you can replace this left hand side part with what? 2R. And here it is 2R and VR B2. That is only B2 is applied. And parallel with series with R and parallel with 2R. This is the voltage you need. Okay, so now listen here. Voltage source series with resistance, parallel with resistance, same as previous case. You can replace that part with what? This part. You can replace with what? Tell me. Yes, here it will be R and this voltage will be VR B2 by 2. This is VR B2 by 2. Okay, this part. Next, remaining as it is you take. What is that remaining part? It is R and 2R. Now again, see this circuit. You have it R and R in series. What is that? 2R parallel with the same. Same or not? So what is the equivalent now? Here, now it will be equal to, voltage source of how much? VR B2 by 4 series with R. Is it clear? This part is 2R parallel with another 2R, same as our shortcut. Half of 2R is R, half of this voltage is VR B2 by half. Okay, so now you can say this is your VA2. What is VA2? Because this current 0, no drop, so you can prove that as VR B2 by 4. Now, similarly, now you can say similarly for B1 it will be VR B1 by 8 and B0 it will be VR B0 by 16. First time it is by 2, second time you got by 4. Similarly, you can prove that third time it will be by 8, fourth time it will be by 16. So now please understand, wherever you are applying the data, first this is always whichever near to your op amp is MSB, far from your op amp will be LSB. So now finally, what is your VA? VA is equal to VR into B3 by 2, VR into B2 by 2. Yesterday class we have discussed everything about what is VR and all those things. V reference, everything. Then VR into V0 by 16. So what is V0 here? 1 plus R2 by R1. 1 minute time, sorry. What is V0 here? 1 plus R2 by, then common VR plus V. Now again, our same method, whatever we have applied yesterday, similar analysis we should apply. It is V0, right? So multiply this with 15 by 15. 1 plus R2 by R1 into VR by 16 into what is this? Decimal equivalent of the binary number. Based on B3, B2, B0, whether it is 0 or 1, you will get that whatever you are having. This part is there now. This will be replaced by V reference by what is that? 15 can be written as 2 power 4 minus 1 into decimal equivalent. That is resolution into decimal equivalent. Here what is V reference? It is 15 by 16 into 1 plus R2 by R1 into VR by 16. Sorry, VR. Okay, or this can be given as FSO. Okay, what is V reference? It is always equal to FSO. Why I took this as V reference? Yesterday also I told, today also I am telling you, just keep all ones here. All ones, if you keep, what you get, it is 15 here. So 15 by 16 into this equation will give you V reference or full scale output. Yeah, your input is digital input, binary input. Your input is generally digital input, means binary input only, on and off only, na? FSO full scale output, yesterday class I told. I have given one slide also. FSO full scale output is equal to VR V reference. What is full scale output? The output when all the inputs are ones. Okay. What happened here? Yesterday class we are missing today, Rushi. What happens? D means decimal equivalent of the input. Please revise, man. Someone have some big doubt. Who is that? 1 minute. Wait. Hussein is having some doubt. Let's clear that. Hussein, why can't we say that R to R? 1 minute. 1 minute, please. Some Hussein is having some doubt. Hussein, previous slide. You are asking this slide or this slide? Please tell me if you are there. 1 minute. Let me clear the next one. Let me clear that, then we can see the remaining people doubt. In this, you have doubt. Please don't comment other things. What is your doubt, Hussein? R to R have same INA. Which are first figure or second figure? Third figure. Yeah, same current. So what? Same current. You can take, what is the problem? You can take all of them in series. You find this current, again find this drop. Okay, same answer will come. Take this voltage by total impedance, and then you can find this current. Then, or you apply voltage division principle, anything will give you a same thing. Yeah, voltage division principle. Okay, but it will be better visualized. It becomes by 4, next time it will become by 8 and everything. Okay, what is your doubt to it? Just wait. Hussein doubt is clear. Decimal equivalent. Can you tell me brief how to find voltage at D3, D2? Okay. ऋषि कल का डाउट कल क्लियर होना चाहिए. Don't leave my class with doubt in your mind. Yes, Udit, tell me what is your doubt. Here you are not finding voltage, you are giving voltage. If this bit is 1, you give VR. Okay. If the bit is 0, you give 0. Like your DI, okay, based on that, if it is 0 or 1, a particular bit I equal to 1 or 0, based on that, you will be connecting that to this. I already yesterday explained. It will be moved from between two voltages, 0 volts and VR. Okay, for 1 and 0. Who will decide that particular bit? Okay. Now, listen here. Okay. We have proved it is working like a DAC. Now, what is the disadvantage in this? Everywhere we have some disadvantage earlier. Now, that previous disadvantage is not there. You have only 2 set of resistors for everything, and also you see whatever may be the input here, you may be giving everything, but finally equivalent resistance will be coming as R only. You check here also. What is the equivalent resistance you are getting? Same input resistance you are getting. Okay, and you can see here. Only one small previous disadvantage is overcome. That is, you used only 2 set of resistors, R and 2R only, not different weights, but still you are able to achieve it. So compared to previous, it is advantage. But still, what is the difference is, yeah, resistance tolerance will be every time there. That is sure. Okay, but there wide range. Here, comparatively, only 2 types. That is the advantage here. And another thing, input impedance is constant here. Okay. Now, Rishi, we applied superposition, then we got this all inputs together. Okay, now see here. Now see here. Now, what is the only disadvantage here is every time you apply the input, as I told here, okay, this bit is 0, you give 0 volts. If it is 1, you give VR. You are giving VR volts. Okay, so every time you are giving two different voltages here. That is, you are switching between either 0 volts or VR. Maybe you are having some switch which is moving between two different voltages, which requires some time to charge and discharge. Or your input requires every time when you are changing between two different voltages, it requires some time for charging and discharging. We can overcome this disadvantage also by using current switched DAC, where you don't switch between two different voltages. I will show you that. Just wait. Let me give you those points. See here. The disadvantage with the yes, VR can be anything. That depends on your wish. Simple rule, Deep. You have some input capacitance. You are connecting this input to two different. Suddenly I connected to ground. I remove it. I connected to 5 volts. Again I remove it. Connected to ground. It requires some time for this charging and discharging of the input capacitance. Yes or no? Because it cannot change instantaneously. When you give the 5 volts, it charges. Again, immediately you make ground. It cannot discharge instantaneously. So it requires some time to switch your inputs. That point is included in this slide. See here. Your total circuit is made of transistors, MOSFETs only. Switching any switch is made of MOSFET. Your MOSFET is having internal capacitance or not at the input? Or yes, Asif, or your op-amp input capacitance you take. Capacitor physically may not be present. Okay, read this. The disadvantage with the voltage switched R to R DAC is every time we apply the input, we need to switch the input between two voltage levels. The input capacitance requires some time to charge and discharge. We can overcome this disadvantage by using current switched R to R type ladder, R to R ladder type DAC, where the switch is moved between same voltage level for both 0 and 1. I will discuss that. Before that, let's do one problem which will give you better feel. So where is this? I think. Hmm, 1 minute. Today I will give you one DPP. Please remind me at the end of the class. Old DPP keys are updated in your group. 1 minute. Where is that? Okay, listen. Let's load the question. So question is loaded. So let's try. Lucky it is there. Tomorrow I'll tell if you want. I have not made the schedule. Sunday I'm taking them. Someone have some doubt? Yes, it will be there, Abhinay. Whenever you are doing transaction between VR and 0, here why problem? It is there. What is your doubt, Aditya? Tomorrow quiz is there, I don't know. Is it weekly quiz? So I will take questions on sequential. I will give questions on sequential. I didn't reschedule, but I generally I'll get message before quiz to upload the questions. I don't know today. I didn't get it. Okay. Anyway, let's come to the question. Let's do it. Prepare sequential. So let's do this question. Shall I start the poll? Your favorite? Ready. Do it. So listen here. What is V naught? What is V naught? Instead of doing that, don't remember this formula. I never suggest you to remember this formula. Easiest, shortest path is 1 plus R2 by R1. What is R2? 7K by 1K into, very simple. Single step is, what is your input here? It is MSB. What is the MSB voltage? 1 volt now. So 1 by 2. Next input is ground, 0 by 4. Next input is again 1 by 8. Next input is ground by 16. Don't say by 32 also. I told this is always ground only. Don't take it as a input. It is a part of design. So now what is the answer? 8 into 1 by 2 plus 1 by 8, which will give you the answer as 5. Very simple. You applied here 1010, you got 5. Okay, suppose, let me do the same question. Let me do the same question. Okay, so suppose you assume this is ground. I'm just changing the question, little small variation, so that it will give you better understanding. Here you give 1 volt, here 1 volt. What is the answer? What is V naught in this case? 1 plus R2 by R1 into 0 by 2, 1 by 4, 0 by 8, 1 by 16, which will give you 2.5. You observe here, the observation is not what about 2.5 or not. Here the input is, here the input is 1010. Here what is your input? 010. That is, your input is here 10. Decimal 10, you got 5 volts. Your input is decimal 5. How much you got? Half of it or not? When input is half, your output is also half. That is what you need to observe here. Okay. So your input need not be equal to this. It is not doing binary decimal conversion. You need not get here exactly 10. What all you need to get it is linear conversion. You get something, you should get something. When your input is reduced by half, output should also reduce by same thing. That is what we call linearity. That is what you require in the design. Your output should be proportional to the input. When all are ones, what you get is called your reference. If you want to calculate here, resolution is asked. You can do it. Only LSB equal to 1, remaining all are zeros. Whatever you get, that is resolution. 8 by 16. Okay. Clear? So let's move. Let me give you same question again. N number of ways I will give you the same question. Suppose if it is 5 volts, this is also 5 volts. Now what is the answer? What is V0 in this case? 1 plus 7k by 1k into, tell me, 5 by 2, 0 by 4, 0 by, what is that? I'm sorry. 1 minute. Let me give you something different way to take this. 1 minute, please. Okay. 5 by 2, 0 by 4, 0 by 8, and 5 by 16. Whatever you get, take it. Answer doesn't matter. I want to give you the concept properly. Shortest way to do this question is gain into whatever the input here by 2, input here by 4, input here by 8 by 16. Okay, here has given 15 volts. Okay, take it as some 30. Okay. Very good. So let's move. Here, I want to give one more small variation in this. Now, it is time for you to answer. Conventional approach, Asif, derivation is done in your class itself. Same derivation, you do it at your conventional exam. Okay, other derivation or use this formula, anything is okay. So, shall we move further? Here, suppose now, listen here. Same question, small change I am doing. Be careful. Guys, get ready. You try it. I will also calculate. Okay, your poll starts now. Mine somehow is the answer like that. Right answer. So here, firstly, what is the answer is some V0 is equal to minus 1k by something. Forget about that something. Yeah, forget about that something. Then 1 by 2 plus 1 by 8, 1 by 16. Otherwise, wait. 1 by 2 plus 0 by 4 plus 0 by 8 plus 1 by 16. Up to this clear, everybody? Minus R2 by R1 is the gain into this part is the same rule. Earlier 1 plus R2 by R1 here. So here different values you keep, you get different answers. So according to Aditya, what I need to keep, Aditya? Please tell me. You said me to check it, so please tell me. Why 1, Aditya? You love it? No, that is a blind way to do the question. That is wrong. Actually, I made calculation mistake, but the B is not the right answer. As most of you liked it, B is not the right answer. Okay, that is where I kept the trap. Okay, here you should take 2. Very good, Hrithik, and who is that? Bhargavi. It is 1K plus 1K. Okay, this is right. I gave the option wrong, but this is the right answer. Okay, so why 1K plus 1K, sir? So you people will argue you me. So let me explain that. So never apply your shortcuts blindly. Whole goes wrong, no problem, but still your 60%, whoever gives the B is wrong only. Don't worry about it. A also given by only some 10-20%. Who genuinely gave A and gave A, those are correct. Even I love. Okay, so let's go here. This is the question we are doing. So whatever. Now listen here. When you apply shortcut, you should find if only, okay, B3 applied. If only B3 applied. Okay, so then what happens? Only V3 is applied means this is also grounded. Now, as we discussed earlier, this story is already done. This part is how much, man? 2 parallel with 2, 1, 1 series with 1 is 2, parallel with 2, 1, series with 1 is 2, parallel with 2, 1, series with 1 is 2K. And the remaining circuit you take as it is. What is that remaining circuit? 1 minute. 1 minute. So 2K, and this one is 2K, and you are having here 1 volt, and this is 1K. This is the circuit. Already I have done this story previously, na? So one parallel with series something whatever. So what will you get? This is 1K, and this will be how much? 1 by 2. Right? So the remaining part is as it is. This 1K, this 1K, this is the V0 for 3, that is equal to minus 1K by Aditya. Please carefully check it. What is that? 1K or 2K? 2K into 1. Okay? समझ हुआ ना? I kept if I don't keep this resistor, if this resistor is not given, your answer is correct. I kept intentionally this resistor here. Okay, don't apply blind shortcuts. So that is the lesson of this problem. This fellow will change your answer. Okay, this is inverting mode. Ajaya? Good. Okay, so little this topic is like that. Your data converters is little network oriented. Okay, little network oriented. Don't be afraid of it. Which one I grounded, man? 1 volt means it is 1 with respect to ground. That's why grounded. That's all simple. We discussed that in the networks class. Don't worry. Okay, leave that. So come to the next part. You are asking this one. I applied only B3 na. I assumed B0 is equal to 0. Superposition. For finding superposition, only one input at a time. Because from one input you can say it will be same for other inputs also. That is the meaning. Okay, why I applied only B3? Why not B0 is I have not solved completely. Okay, I have not solved completely, which is not required. Once you get this, you can apply the shortcut. You understand the gain now. From that, you can apply gain into this part. This is only for B3. Similarly, you can do for B0 if you want. So let's move to the next one. Okay, so let's move to the next one. Now, what is that? What is the disadvantage I told? We are moving the switch between 2 voltages, 5 volts and 0 volts. So because of that, it is taking time to charge and discharge. This is the disadvantage with the any voltage switch DAC. So we can overcome this disadvantage by using another kind of DAC called as current switched DAC. What is current switched DAC? Let me draw it. So let me draw the circuit. Topic it's here. Also, I'm not having actually enough time to concentrate. Also, yeah, in English also, sir will take. Don't worry. Kamesh sir will take it. The class to be fun like that. Okay, I'm just kidding. Yes, Pupul. Also, we can manage the time provided if you study properly. Okay, then this is bit 3, bit 2, bit 1, and bit 0. So these are the switches. Now this is ground na 0 volts. This is also ground na 0 volts. All grounds are connected. By virtual ground, what is this voltage? This is also 0. This is also 0. So now, if your logical input is 1, what is this? Logic. Okay. If it is logic 1 or logic 0. Take my class with you, Aditya. Logic 0, logic 1. Okay, you understand that here it is for 1 and 0, 1 and 0. You understand here for 1 you will be connecting here, for 0 you will be connecting. Okay, now first point you can observe here is the switch is moved between these two positions. Whether you connect it here or here, connect it here or here, anywhere you connect it, your voltage is the same or different. Voltage is saying same. Voltage is saying same only. Voltage is saying same only. That is, there is no voltage switching here. There is no voltage switching here. That is clear. Whether it will work as our required condition or not, that we need to prove. That is our job. Okay, we need to prove that whether this fellow will work for us or not. Firstly, one thing is clear. What is that? There is no voltage switching at all here. If it is 1, I connect here. If it is 0, I connect here. Okay, now let me take this current as I in. Ideal op amp current is 0. So this current is also I in only. Okay, let me take this current as I. Now, okay, start from bottom. So whether you connect it here or here, it is 0 volts only, and this is also 0 volts. So these two are at same node voltages. So 2R and 2R are in parallel. Whether you connect it this ground or this ground, whether it is both of them are in parallel. So what is the resistance equivalent? 2R is parallel with 2R will give you R. Series with R, 2R. Again parallel with 2R. Series with R, 2R, parallel with 2R, R. Series with R, 2R, parallel with 2R is R. So this total is equal to R. This total impedance will be equal to R. So what is your I is VR by R. Now come down. I told total is R. Now this part is 2R. This whole part is 2R. So you can divide the current into equal parts of I by 2 and this is also I by 2. Because current is same, because impedance is same, current divides equally. This will divide into I by 2 and I by 2. Current I comes, it divides I by 2, I by 2. If I by 2 comes, current divides into I by 4, I by 4. Why equally dividing? Because don't see this resistance, this total resistance and this resistance same. Again I by 4 comes, this will divide into I by 8, I by 8. And this will divide into I by 16 and I by 16. That's all. So this is how current gets divided. Now our job is, so when a particular bit is 1, this current will be going through this path. If particular bit is 0, it will go through the ground. So current is getting switched. Whether it is 1, it will may go through this resistor. Otherwise, it will go through this. So that is what happening here. So now what is V0 is equal to minus IN into RF. What is V0? You take this as IN because this is 0 volts now. By KVL, you can say this voltage is this. Okay, by KVL, this one only minus IN into RF because this is 0. Okay, what is V0 is minus IN into RF. Okay, now what is IN? What is IN is, see here, if a bit 3 is 1, you get a current of I by 2. So can I say like this? If bit 3 is 1, you get a current of I by 2. So can I say bit 3 times I by 2? Because bit 3 is 1, I will get I by 2. Bit 3 is 0, I don't get anything. Similarly, bit 2 times I by 4. Bit 1 times I by 8. And bit 0 times I by 16. Okay. So now again, what is your IN? You take I by 16 common. What is I? VR by R. Substitute it. Minus VR by 16 into R into RF into 8B3 plus 4B2 plus 2B1 plus B1. You understand this? I replace I with VR by R, multiply with RF, you got V0. Just a normal mathematical equation part. So this part can be replaced by what? What is this? It is nothing but D. D for decimal equivalent. Okay. So now listen here. V0 is equal to multiply by R into part, whatever you are having with. Okay. So what is V reference? Here 15 by minus 15 by 16 into VR into RF by R. This is how you can control your maximum voltage you will get. These are the parameters which are in your hand only. That will decide what is the maximum voltage you will get it. And your resolution, everything. V reference, okay, and resolution. Number of bits is decided by these resistors and resolution will be calculated. The max full scale output, everything is decided by this V reference, which is in the hands of RF and R and this VR. Is it clear? So here there is no voltage switching. What we are able to make this V0 is equal to RD condition. V0 is we are able to make this V0 equal to resolution into decimal equivalent condition. Okay, fine. Shall we move further? Very good. We are discussing only ideal case as if, okay. If you take care of all those things, then it will become your analog clocks. Okay, there will be the design issues that we will overcome accordingly. Okay, so compared to previous case, we are able to do better. Okay, this method is not failed. Why it is failed? Okay, yeah, every time for you propagation delay is very important. Propagation delay of the circuit, mostly we take care of your RC time constant tau only. Okay, this is more dominant in the circuit. That is input charging requires. Who is stopping that input charging is stopped by generally the capacitors. Okay, so the next one we are going now. Please listen. These are the three different D2A converters we have discussed. What are they? Weighted resistor type. Second one, R2R ladder type in that voltage switched and also current switched. I have given the heading or not? No, I'm sorry. Current switched R2R type DAC. Okay, this is your current switch R2R type DAC. Right, let's do one question. Current division same, simple here. Two resistors are equal, current divides equally. If this is R and you add this, you get 2R. This whole is 2R, this whole is 2R. So current is dividing equally. This is 2R and parallel with the 2R will give you R. Series with R is 2R. This is 2R and this is 2R. Current divides equally. Same, this whole is R. Series with R is 2R. So this whole part is 2R. Okay. And the remaining part is 2R. So current divides equally by 2. So starting by 2 by 2, by 4 by 4, by 8, by 16, by 16, and so on. Okay. So let's go to the next question. What happened? You must fail to load. Please go back to class. No need. We should remind the logic by 2, by 4, by 8, by 16, like previous question. We should remember the logic. So that's why I gave the question based on this. So let's start the question. Now, read the question. Current I. We follow this. I use that VR, he used the VN, we take the VN, whatever. So if you're ready, we can start the poll. Ready, guys? Right. You can take none also if you want. Start the poll. Very good. Robert, very good. Anupama, Rudraksh, Amitabh, Sagar, Rushi, Vasista, Ganshu, Pratik, and Rohit. Sorry. Yeah, let's do. It's a simple question. What is the current I? I told the formula now. What is the current I? V in by R. You see 2R, 2R, R, 2R. Okay, you should see the structure, you should remember. Okay, so what is V in by R here? 10 volts by 10 kilo, which will give you 1 milliampere. Now, you take this current as I, okay, or I, capital I. Then this will be by 2, this also I by 2. 1 minute. Okay. This is I by 2, I by 2. What is this current? I by 4, and this will be I by 4 again. Okay. So again, what is this current? I by 4 comes here. It divides into two parts. I by 8, I by 8. This I by 8 divides into two parts. What are they? I by 16, and this I will be equal to I by 16. This you know, last branch will be I by 16. Okay. So now listen here. So what is your small I? It is capital I, that is 10 power minus 3 by 16, which will give you 62.5 microampere. Single step you will be getting the answer. Okay, ready? Shall I start the next question? Magna output V0, I don't say because it is the next question. Okay, so that is the next question. What is V0? It is a two questions gave in one of the gate paper for 4 marks. Okay, so get ready guys, start. Let me start. Shall we start or the poll, or you wait? Shall I wait for 1 minute or something? You do the calculation. Find V0. Very good. Howard, Deep, Mohan, Rudraksh, and Sura. Right. Very good. Well done. So you can see here, same story. Already previous we have done now. So this will be I by 2, I by 2. Here you get I by 4, I by 4. Here you get I by 8. This will be I by 8. And this will be I by 16. I by this will be I by 16 and I by 16. So what is this current? IN, okay, or I naught. What is I naught is equal to, these two are entering now, so I by 4 plus I by 16, which is 5 by 16 into I. What is V naught? Minus R into, okay, so minus R into 5 by 16. Okay, so what is R value? minus 10k pi by 16 into I. What is I? Already previous we have calculated 10 power minus 3, which will give you minus 3.1. Single step answers. Okay, that is already previous question we have done this analysis. Use this and this, that will go this. Okay, so that will give you whatever you get, that you can apply minus r into I. Same, if you understand the theory properly, you can answer both the questions. Any doubt, ask me, otherwise we'll move to the next. Very nice. Looks like circuit theory. So the next question. Question is not loading yet. I don't know, some issue is there, maybe question is not uploading. What to do? Let's change the slide and try. Okay, let's finally tested my patience. So bad server, something, finally I got it. Welcome back to you also. So let's start. Thank you. Am I not visible? Refresh, guys. Okay, let's. So that bad. I think who gave me that idea to refresh? Who is that? Sura, I think. You made that guy. So that question, I think it won't get loaded. It again, same thing is coming because of that. Let me load some other question and check it. It's happening or not. Let me load the same question, for example. Yeah, I think some issue is with the uploading questions only. So let's continue with the next part. Then tomorrow anyway we have doubt session. We can discuss the problem. Okay, more problems we'll discuss after the theory also. So the next one we are going to discuss is the next one we are going to discuss is ADC. What is ADC? Analog to digital converter. In that we are going to discuss 4 things. So analog to digital converters. In that first one is counter type ADC. Next, flash or parallel comparator type. The next one we are going to discuss is successive approximation. And the last one we are going to discuss, according to our gate, dual slope integrator. So these are the different ADCs we are going to discuss now. So the first one is we are going to discuss is this one. What is that? SAR, successive approximation digital. When it comes, we discuss anyway. That's why I haven't written. Don't worry. Counter type. So the first one we are going to discuss now is counter type ADC. Okay. So in the counter type ADC, let's see what is this counter type ADC. If questions are not getting loaded, how can I give you DPP? No problem. I need to give you DPP for tomorrow's discussion, right? I hope it will be fine by that time. Oh, it's loading. Right. It's loading. So I think you don't like that particular question. So this is what we call counter type ADC. Log out what? Okay, counter type ADC. This is the circuit. How it will work, I will explain. Just listen. Is it lagging? Okay. Fine. Let me explain. So this is what we call counter type ADC. Let me take, for example, it is a DAC with a step size is equal to 1 volt. Okay. And let me take input is equal to 6.2. Prakash, message me in Unacademy. I can help you. Don't worry. First message me there. Or any of our students can also add you. So now listen here. So whenever I want to start this conversion, I give one pulse like this. What is this pulse? It will tell you to start the conversion. SOC signal. It is just like SOC. It will start the conversion. That is, start the conversion means make all bits to 0. It will make every single bit here to 0. Now, what is DAC means? For DAC, you give this all zeros. What is the output you get for DAC is 0. 6.2 is more or 0 is more? 6.2 is more or 0 is more? 6.2 is more than 0. So I will get here 6.2. I will get here 6.2. Sorry, why I'm saying 6.2? I'm sorry. I will get here 1. 1 into clock will be applied. When its edge comes, then I will get 1. Then I will get, assume step size is equal to 1 volt. So 1 volt will come here. 6.2 is more or 1 volt is more? 6.2 is more, na? So you get another one here. So you will again get the clock. So like that, this process will be repeated. Here also you get 2, 3, and so on. 6. 2 volts. Okay. And so on 6 volts, the same story will happen. So this will be 1 only, this will be clock. Okay. So after 6, okay, so clock 6 volts will come and then you get clock again, then you will get now next bit, that is 7. Now for 7 will come. Okay. 7 will come, then you will get 7 volts. Okay. 7 volts will come. 6.2 is more or 7 is more? 6.2 is more or 7 is more? 7 is more, na? So you will get 0. This is less than this negative. So comparator will give 0. So the clock will stop. So the counter will lock. So once this is done, this 0 will tell you end of conversion. As long as it is 1, conversion is happening. Whenever it becomes 0, it is doing end of conversion. That's why I name it as EOC bar, end of conversion bar signal. When it is 0, it will tell that conversion is done, man. You read the data. Because you should not read the data here. No? In this space, you should not read the data. Okay. SOC is start of conversion. E is end, S means start. Start of conversion. To start, I should clear the previous data. So I can give this pulse, then it will clear the data. Okay, during this period, I should not read. So I will use this end of conversion signal. Whenever it becomes 0, I enable the output device to read the data. Okay, you understand here up to this? So this is what you get it as the digital final output. This is the final output. Okay, now wait. This is how it is doing. In this process, some error is there. What is the error? Actually, your input is 6.2, but I represent it as 7 only. So that error is equal to 0.8. Okay, that is a 7 minus 6.2. You can see what is the maximum error. It is having one technical name called quantization. What is the maximum quantization error you get is equal to 1 step size. In this case, say 1 volt, 0.9999 something, you can take it as 1. It may be 6, you may represent it as a 7. Some small 6 point something, you may represent it as a 7. So you can say all maximum you can have 1 as your step size. I mean 1 as your error. So if okay, step size is reduced, then what happens? If step size is reduced, then quantization error will reduce. Maximum quantization. What is this? QE, quantization error. Okay, so you understand here, when this input is greater than this input, you get 1. When you get 1 into clock will give clock in the output, then clock will be allowed. Whenever this input is less than or equal to this input, you get 0. Okay, step size is taken here 1 volt now, step size of the DAC. In the ADC, in the feedback, we using DAC to compare your output with the input. You understand? It is ADC only, but inside you have some DAC also. Maximum error is not 1 point. What happened, Nishita? It is 1 step size. It is not 1.55. Okay. Right. So here one more thing. Let me write here. What is the digital output? For example, listen only. Yes. If step size is equal to 0.5, then what happens? If your step size is 0.5, what happens? You will get 0, 0.51, 1.5, 2, 2.5, 3, 3.5, 4, 4.5, 5, 5.5, 6, 6.5, it will stop. So in that case, what is the error? 6.5 minus 6.2, so 0.3. So error reduced or not? Right. Okay. So yes, VD depends on step size. Na? It is DAC we have discussed. Resolution into decimal equivalent of this will come. RD. So now listen here. What is the formula for digital output you are getting is given by ceiling function of analog input by resolution. It is not, I didn't forget to make this bracket. It is called ceiling function. It will give you round off value. Okay, so for example, your input is equal to 6.2. Step size is equal to 1 volt. What is the digital output? It is a ceiling function of 6.2. Dhanpal, please wait, everybody. I mean, Dhanpal 1, which will give you 7. That is 0, 111 is the answer. You got that, now? 7 is the equivalent, you should convert into binary. Next, your input is equal to 6.2 only, step size is equal to 0.5. Then what is the digital output? It is ceiling function of 6.2 by 0.5. I asked digital output, not DAC output. Digital output is this. So it is a ceiling function of 12.4. 12.4 का ceiling function क्या? Wait. It will give you 30. That is 1101. So depend. I already told you, your output need not be equal to input. It should be linear function of input. Okay. Some Dhanpal, you have any doubt? Ask me. Okay, clear. Wait. Listen. Now I will give you one challenge. You do it. Tell me. I want to improve quantization error. What to do? Don't say, sir, I will decrease step size. No. Step size should be same, but still I want to improve quantization error. What to do? Is it clear, my question? Firstly, my question is clear. For the same circuit, I do little modification. Why down counter here? It may be easy. Don't see only 6.2. Take 6.9. Anything it should work. VA is not in your hand, man. VA is the analog input coming from something. Don't say, sir, 6.9 I take, sir, here 7. No error will come, sir. Don't say like that. That is not your solution. How to do that, Asif? That is what I am saying, asking. How to do that? I want to improve the quantization error without decreasing step size. It doesn't matter whether clock pulse is negative or positive, it will work in the same way. Clock is not having anything with quantization error. Clock will tell you delay only. What is decimal point, Deep? Someone told, okay. More number of bits means you are changing resolution again. Resolution should not be changed. Resolution change anyway, you get the better answer. What is that other gate? No. Step size can be, I told step size is this much only. Step size is decimal or not, doesn't matter. You decrease step size, quantization error decreases, that is sure. If you use OR gate every time clock, circuit will fail, man. Sushil, if you give OR gate, circuit will fail. Clock, whenever clock is 1, it will go. Hint chahiye. Think like that. Suppose you should design like that. Okay, small variations you do. You may use some circuit. Think like that. Whichever, suppose in this case, suppose if I am able to stop the counter at 6, it is advantage. Do something and stop your counter at 6. I am saying please listen, it should work for 6.9 also. Okay, you should give the answer such that it is synchronous counter only, man. Why, Dhanpal? Whether it is a 6.2, I should get 6. If it is 6.9, I should get 7. Okay, your answer should be like that. Your answer, don't change the total circuit. Don't say, I use some other counter, what we call some other ADC. You understand my question? Do something such that error is always less compared to. Okay, you do whatever you want. No, what do you do with integrator? Wait, let me give you one circuit. You tell me whether it will do it or not. I didn't get any right answer from you. Okay. Now see, I'm not saying to change the counter at all. If you change the count, sorry, ADC, it will do something. Now listen. Now listen here how it will work. You give SOC, it will make all zeros. Then you get 0 volts. So here I add some 0.5 volts. Step size is equal to 1 volt. So here by default, for every value coming here, I'm adding 0.5 and giving it here. I don't compare with 0 at all. I compare with 0.5. Okay, that is a half step size. Now 6.2 and 0.5 you check it. What will you get? 1. So your clock will be applied. Like that you get 1 up to 0, 0, 1, 0, 0, 0, 1, 0, 1. 5 is there now. For 5, 1 volt, 2 volt up to 5. Okay, you apply 1.5, 2.5, up to how much you get? 5.5. 6.2 and 5.5 you compare. 6.2 is more, you get clock. In the next clock, what happens? Next clock, what happens? Here you get 6. Then you get 6 here. Then what will you get here? 6.5. Stop. So 6.2 and 6.25, you get 0 here, 0. Lock it. In this case, maximum quantization error is equal to 0.5 or half step size. It is equal to half step size. 1 minute. Offset is the value you are adding here for the input. This is the technical name for this is called offset. In measurements and control systems, you use it. Again, what happened, Anuj? You came today now itself, or you are there in the class? Wait, yeah, wait. Stop discussion. Just wait. Okay. You take here, for example, 6.9. Now what happens? 6.9 is greater than 6.5 now. So it will count here also. Then you will get what? You will get 1 and it will count 7 also in that case. And you will get 7 here. Then what will you get? 7.5. Then it stops. So in that case, 6.9 and 7, what is the error? 0.1. So you understand, if your input is more than some, okay, 6.5, it will give 7. If it is less than 6.5, it will give 6. That's why half is taken. That is half step size is taken. That is the reason, you understand. If your input is below this, then it will give the lowest value. If it is above this already, then when you add half also it is still above, it will give the next value. That is the advantage here. Why can't you add 0.25 or 0.25 may work for this question, not for every question. For any random input, it should work. That is our intention. Whether it is 6.9, then it will give 7 is advantage. Say 6.6 is there, then it should give you 7 only. 6.4 is there, it should give you 6 only. What is that point to, man? I didn't get you what you are asking, Aditya. Forget about this input. For any general input, okay, in this case, error may be 0.2, that doesn't matter. Maximum means what? Worst case for any input. Now, any doubt, ask me. The optimum value here is half step size. That is the best thing you can do. That is how you should think. Don't think for only one input. It should be for any random input, it should work like that. In that, okay? So, like this, if it is in the range of 6 to 6.5, I will give 6. If it is in the range of 6.5 to 7, I will give 7. And now here, instead of taking 6 and 7, upper and lower limit, we are taking from the middle. This you do in your communication also. Okay. So this is the best thing you can do. Quantization. This is what we call quantization. Quantization means what? You giving the output to the nearest possible value. You cannot give 6.2, so you should give 6 or 7. So in that, whichever is nearest to you, 6 is more nearest. So in this process, whatever you are losing the data, that is called quantization error. So anyone having doubt, please now ask me. Some addition, it should add some 0.5 volts to this input. 0.5 in the sense half step size. If it is step size is 0.5, you should add 0.25. Step size is some x, you should add x by 2. It should add half step size to this value. You should use some kind of summing circuit or something which will do this. Sir, if input is 6.5, okay, if it is exactly same, then it depends on the comparator. Comparator will firstly give you the specification V1 greater than V2 1, V1 less than or equal to V2 0. Like that, comparator will tell you, or V1 greater than V2 by some 0.1. It will tell like that also. It depends on the comparator. Some threshold it will give. If it is minimum 0.1 greater, then only 1, otherwise 0, like that. Maximum means for any input. Okay, Alisha? You give 6 as the input, what is the output you get? See here, Alisha, 6.51, you have this input. Okay, Alisha, please see. You give 6.51. Okay, 6.51 is more than 6.5 now, so you will get 7. It will come 7.5 and stop. In this case, what is the error you will getting? You are there or not, Aditya? Please tell me. That is the maximum worst case possibility here. Any other doubt? Please ask fast. Aditya, you understand or not? Please comment. Remaining people, is it clear? So you understand, this is the advantage if you add small offset instead of decreasing step size. Decreasing step size means, see here, if you want to decrease the step size, you should go back in the design. Either you should increase the what we call decreasing step size means number of bits maybe need to be increased, or one thing, or you should improve the reference voltage. Reference voltage formula I have given, these parameters are to be improved. Instead of that, simple thing can be done. Offset is extra you are adding, not the input. Please understand, extra you are adding. Now, this is what we call offset. Chaitanya. So if your input is 6.5, according to the design, it may stop at 6.5 or 7.5. It depends on the design. If comparator gives 6.5 and 6.5 may 1, it may go to 7.5. In general, you can say it will stop at 6.5 itself. Then you get answer is equal to 6 only. Generally, it is like that. V1 greater than V2, 1. V1 less than or equal to, it is 0. Even it is for equal also, you get 0 only. If nothing specified, this is the format we follow. Okay, that is about your comparator type ADC. So that is about today's class. Problems are to be done. Wait. Yeah, DPP will be given. Read these points. Bhargavi, please don't think for this input only. Think for any random input, it should work. Okay, you take 6 point. See, don't say, sir, I will give here 0.2. Then your error will be 0, sir. No. Don't think of this input. Think for any input, it should work properly. Okay, if you take offset of 0.1, what is the advantage, man? 6.1 only. 6.2 greater than 6.1, still clock will be 1. It will count 7 also. No need of sorry, please understand that. For your design should be for any random input. Here, what I have taken 6.2 is just example. Was it if it is 6.5? Okay, so both are 6.5. This comparator will give you 0. In that case, also it will stop at 6 only. Only if it is greater, then only it will give what we call 1. Okay, read this. In a counter type ADC, it is allowed to count as long as the analog input. Please see, the analog input is more than DAC output. That is VA greater than VD. Next. When DAC output is more than the analog input, the clock input to the counter becomes 0 and the AND gate output becomes 0. Okay, right? See, 1 minute. Quantization error is difference between this and this, not this and this. Okay, quantization, because your output is represented by this fellow, not this fellow. Even it is 6.5. Okay, here it is 6. The error is between these two, not these two. Okay, Aditya? 6.5 may stop hua, sir. Okay, don't take error between these two. It is between these two. Yes, to reduce the error means maximum error is in the first case it is 1 volt. Now in this case maximum error is how much? Half volt. So see here, in counter type ADC it is allowed to count as long as the analog input is more than DAC. When DAC output is more than the input, then it will stop. Okay, counter output is proportional to the magnitude of the input. It is called single slope ramp type ADC because it is counting one direction only, up only. Okay. Next, clocks are not reduced, Deepak. Okay, it may reduce by 1 maximum. It is also called as a single slope or ramp type ADC. We can add offset voltage of half LSB. See that 0.5 LSB. It is not 0.5 volts. It is because step size is 1. You took 0.5 earlier. 0.5 LSB to the output of DAC to improve the quantization error. Disadvantage with the counter type ADC is here one disadvantage is there. What is that? If you take small input, it requires less time. If you take big input, it requires more time. So the conversion time is dependent on magnitude of the input. That is, it is not having uniform conversion time. So it is not suitable for applications like data acquisition systems. What is that? I will tell you, just wait. We can overcome this disadvantage by using a counter called, ADC called SCR, that we discuss next class. Now see here. What is the conversion time you have? Maximum conversion time here is, counter will count maximum how much? 2 power n minus 1. Because the counter will count from all zeros to maximum all ones. Now, what is the conversion time average? What is average conversion time is given by, suppose your input is very small, it may require 1 clock only. Little more, it may require 2 clocks. Little more, 3, like that, maximum 2 power n minus 1 by total, by average is total different possibilities by total number of samples. How many number of samples here? This will give you average. So what is the formula? N into n plus 1 by 2. This is a mathematical part. Don't, okay, I hope you don't have any doubt in this. Then what is the answer? 2 power n by 2, which is 2 power n minus 1. Okay, here a minus 1 is in the numerator, here it is in the outside. So this is the conversion time on an average. If exam may he asks conversion, nothing specified, we should take this only. If he specify average, we should take this. Unless he specify average, we don't take this one. Understand this part? Yes or no? Please tell. Okay, wait. One more thing, just 2-3 minutes, I will leave you because it will be complete after that. So your DPP is to be today's 17th. Okay. Just wait. Today's DPP. Some questions you may not be able to do it because of these topics not done. Reminding you to. Okay, wait. What happened? Yeah, tomorrow I will solve. So today you try. Okay. So listen here. 1 minute. What is the disadvantage if your conversion time is not uniform? For some input it is sometimes, for some other input some other time. What is the disadvantage in this? See here. Suppose you have some kind of random analog data. Say temperature is there. You are converted into analog, some digital, some analog signal like this. This temperature data you want to find. Here you take the input. You got the output after this time. Again you take the input. You got the output after this time. For this input you got the output immediately. For this input you got little late. If you get the conversion at a different time instance, what is the disadvantage? So this at T1, T2, T3, T4 and T5. Here, if I get this data at a different instant, I have some disadvantage. What is that? I need to store magnitude. We need to store magnitude and also time. Okay. So I need to store here magnitude and again at what time it is. Again I should store this because to retrieve back the data, okay, because for storage purpose I use digital signal processing, okay, or for processing purpose. So I convert this data into digital format. So only information time is not sufficient, or sorry, only magnitude not sufficient. Here I need to store time also. At this time this much, at this time this much, at this time this much. Okay, suppose you have like this. That is, for equal times you are getting the data. Here only magnitude enough. Okay, since time gap same. So if you know first is 1 hour, second by default 2 hours, 3 hours, 4 hours, 5 hours, 6 hours, 7 hours. By default, you can say if you know the sample number from that, you can find the time. You need not store the time. Okay, here you need to store the time every time, or you should not to wait for the maximum possibility. Then you need not to worry about the time. But here you are getting uniform conversion time. Okay, in the first case, you need to store time and magnitude. Here, you should store only magnitude. This kind of system is required for some systems called data acquisition systems. What is that? Data acquisition systems. What is data acquisition systems? Are like temperature, weather reporting, etc., where they will collect the data. They will collect the data. Okay, and they will be storing it in the digital format. They will use it for digital signal processing for their analysis, etc. They may be using it. Okay, so because your nature is in analog format, first they need to convert it to digital format. Suppose you have a huge more memory. If you take only magnitude, where time is by default same, time gap is the same, then these kind of systems are suggestible in which kind DAS. That will be used in SAR that we discuss later. Now you understand the disadvantage or not? You understand the disadvantage or not? Okay, it will give you at different timestamps. It will give you uniform timestamp. This is done by SAR that we discuss tomorrow. Tomorrow in the sense next class. Don't worry about it. Okay, so this is one disadvantage. So conversion time is here maximum time. We generally say 2 power n minus 1. If you take average, that is one for first signal 1, second signal 2 time periods, third signal 3 time periods. All possibilities I write by number of samples will give you average. That is n into n plus 1 by 2 into this value will give you 2 power n by 2 is the average conversion time. Okay. So now lastly, one more point. Please bear with me because it is a continuation. I don't want to discuss it later. If we complete it, it will be good. Not much time. For example, your input is right. So earlier we used only up counter now. So if you use up counter, for example, your input is 2.2. So I will count, say for example this. Then again input is some 4.5. This is just a, for example I have taken. Okay. Now the new input comes, say some 1.8. Again new input comes, some 4.9. Like this, some different inputs are there. Every time it comes to, this is counter type ADC. For different inputs, every time it becomes 0, SOIC, 0 and go. I will use another counter type ADC called tracking type ADC. There I use some circuit such that your input is how much? Say 2.2. When the next input comes as 1.8, I don't go to 0. I simply decrease by 1 step. After 1.8, now new input comes. Then what I will do is just increase from this level only. Okay, what is the advantage here? It can save some time or not. Here also there may be disadvantage. You may be at the peak, it may be zero, it may come back and do it. That is there definitely. Okay, but here what is that? It depends on the data. Every time may not be saving time, but most of the cases it will save the time. So here what is that? Sampling. Okay, here what is the advantage? Sampling time. What is sampling time, sir? The output, the time between two successive samples decrease, and sampling frequency increase. Okay, so you understand here. These are the three different inputs you are having. Assume these are the three different inputs. Listen carefully. If earlier case, once it counts, it should go to zero and count again. Go to zero, count again. What I am saying is, why to go zero? Use one kind of counter called up down counter. It will compare 1.8 is more or less. Then from here itself go down. Why to go to complete zero and come back to 2? Why to go to complete zero and come back to this? Instead of that, just decrease one step. Maybe your answer comes depending on your step size. So the new input comes. If it is more, increase. If it is less, decrease from that point itself. From that point itself, which can save our time. Already we have spent this time. That can be used now. It may not save every time, but most of the cases it can save. Aman, is it clear? So the time between successive outputs is called as sampling time, is decreased in this case. Okay. So that is about your counter type ADC. Tomorrow we will be discussing what we call the other parts. Tomorrow doubt discussion we do that DPP and other questions. Few questions we will be doing it. So tomorrow questions I will load. Listen. Okay. Yes, my brother kid. As if you are having good observation. Okay. Some few questions I have uploaded as today's homework. Okay, tomorrow I don't discuss new things, but all these questions I will be discussing. I don't discuss in the doubt session, I never discuss new topic, but okay, I discuss these problems. All these good problems we'll be discussing tomorrow. Just go back. Who is that? 1 minute, 1 minute. Some people face difficulty here. Let me explain this again. For those who are having difficulty, remaining people can live happy. Thank you very much. What happened, Aditya? One minute. Wait, wait. Type PDF. What is that? Aditya, which one? Disadvantage with the counter type ADCs, its conversion time depend on magnitude of the input. It is not having uniform conversion time. Last line. We can overcome this. Okay. We need to overcome not advantages, disadvantages. Correct. Right. So those who are having any doubt in this part, you feel any confusion, ask me. I am happy to help you. Remaining people can leave the class. Up down may you replace this with up down, and you should do one more thing. Here you should have some kind of comparator circuit again to compare the previous value, I mean previous data input and new input. Every time you should have some decision making circuit. If previous and new are different, I mean previous and new are previous is more than new, then we should go up or down. Previous is less than new, we should go up or down. Up and down control will be controlled by that decision logic. You should have one decision making circuit that will decide based on previous value and new value. Here actual sense input is not constant for this much amount of time. We use one circuit called sample and hold, which will sample the input and hold it up to the end of the conversion. So Rahul, what is the question? Here quantization error is difference between quantization error is the difference between this and this. What is quantization error? Is VD minus VA. Anyway, same answer. Any other doubt, please ask. Then we can end the session otherwise. Sure, Prakash. If it is no other doubts, we can end the class. What happened? Okay, good night. Bye-bye. It is used. I have not shown also. Offset is the extra voltage you are adding. It is just technically we can say extra voltage you can add here. Okay, this is not part of your system now. You are adding this extra. This name is called offset. How much you should add optimally is half step size, such that if your input is between 6 to 6.5, it will give 6, 6.5 to 7, it will give 7. Yeah, at the adder, you are adding this voltage now. This is what we call offset. Thank you. Thank you. Good night. Thank you. Good night. Good night. Good night, everyone. No more doubts. Now, anyway, tomorrow is doubt session. In anyway, if you have doubt, you can ask again also tomorrow. Just go through today's lecture. Any doubt in this today's session, tomorrow we can discuss again. So thank you. Let me end the class.